All right, here are some of the basics of analyzing waves in air. The first thing to realize is that the amplitude is simply the displacement of the waveform from zero, or from a neutral position. A lot of time that's measured at the point of maximum displacement. Amplitude relates to intensity, but we won't be covering that in this video here. When you're adding waves together, you add their amplitudes to each other, and that can result in interference patterns. Constructive interference is when the two waves serve to exaggerate each other and both of them are moving in the same direction at the same time, and so those will have constructive interference. When it's destructive, those waves will be dampening each other. Now, probably the most important formula to know for any wave is that the velocity of the wave equals the frequency times the wavelength. And this equals c in most cases. C for light is going to equal 3 times 10 to the 8 meters per second. Commit that one to memory. And c for sound, the speed of sound, is 343 meters per second. Some use 340, some use 330. It's unlikely you'll be tested on this exact number here, but this is the speed of sound, and you should at least know the order of magnitude that you're dealing with there. So the frequency times wavelength of any photon, any light wave, is going to equal 3 times 10 to the 8th as long as you are in air and not passing through glass or some other medium that might involve a change in the speed of light. The period of a wave is the reciprocal of the frequency of that wave. And what the period means is it's the amount of time that it takes for one wavelength to cycle through, so for you to complete an entire waveform, or for, if you're looking at a particular point in space, for one entire waveform to pass that point and begin the next wavelength there. So it's the time that it takes for a wavelength to cycle through or pass a given point. And one thing that's very important because of the dual nature of light, remember, light behaves like a wave, but it can carry energy like a particle, and that is the dual nature of light, that it exists as a waveform but also can carry energy as though it were matter. The energy carried by a photon is equal to Planck's constant times frequency. Now, Planck's constant is 6.626 times 10 to the negative 34. You're unlikely to be tested on that, and if you're doing the MCAT, that will be provided to you. But do realize that there's a positive relationship between the energy of a photon and its frequency. This can be useful for analyzing a lot of different light-based questions. For example, ultraviolet light, which is something that can actually burn skin, exists on the violet side of the spectrum, and that is the light that has higher energy. It's the energy that can burn, and thus the violet light is the type of light that has a greater frequency. Infrared light, like that coming from a TV remote, is not something that can do damage to skin, and it tends to be a lower form of frequency and thus a lower form of energy. So red light is the one with the smaller frequency, violet is the one with the greater frequency, and you can look at that in terms of energies. Sometimes people look at flames. The blue flame is hotter and has greater energy, and so the violet one is the one that once again carries the greater frequency and greater energy. And there are various mechanisms for this, but do realize that there's a direct relationship between frequency and energy. And as soon as you realize that, then a lot of calculations involving the light spectrum become a lot simpler. So these are the major basics that you need to be considering when you're dealing with waves existing in air.